Hi, welcome back to Mathematical Logic. In this video, we're going to talk about inference, rules, and deduction. So we've seen so far two different inference algorithms. The first one was model checking, and the second one was Tableau Trees or refutation trees. In model checking, essentially, we just use a brute force attack and just check out all the models that satisfy a certain sentence. And we use that to also make a deduction by checking for entailment. Essentially, what that uses is this deduction theorem. It says that P entails Q if and only if P implication Q is valid. And so, if we were to write a program that use this inference algorithm, we essentially will basically check for this the validity of this statement, and then the other method that we talked about was the Tableau Trees, which basically used the following result. If you want to check for entailment with this method, then to show that P entails Q, we have to check to see that we want to show that P and not Q is unsatisfiable. If P and not Q is unsatisfiable, that means that that P must entails Q, because they can P and not Q cannot occur together. And so proving Q from P by checking for the unsatisfiability of P and not Q basically corresponds to a technique in math called proof by contradiction, or reductio ad absurdum, which is Latin for reduction to an absurd thing. And so this is also known as proof by refutation or proof by contradiction. In fact, we call these trees another way to describe these trees by saying these are refutation trees. And so use this method. And we saw last time that we basically expand the tree until and show that if the tree is closed, then we do have entailment. An inference algorithm that derives only entail sentences is called a sound or truth preserving. Soundness is essentially saying that our algorithm can only derive conclusion that actually entailed by the knowledge base. An unsound algorithm would be one that kind of makes up its own rules as it goes along and doesn't really give us sentences that are actually entailed by a knowledge base. And it's easy to check that if you have a space of finite models, like a finite number of symbols, for example, then model checking and Tableau Trees, these are both sound algorithms. And then completeness is another property that we want to have in our inference algorithm. And an inference algorithm is complete if it can derive any sentence that is entailed. In other words, if you have a knowledge base and suppose you have a statement that is logically entailed from your knowledge base, then the inference algorithm can derive that sentence. We'll explore some of these, both these ideas in the homework. And again, model checking and Tableau Trees are also complete algorithms. That means that if you have a statement that is entailed by a knowledge base, these methods can prove entailment and can make that logical inference. Now, so most of that other stuff is basically trying to find, try to check models. A lot of it has to do with looking at truth table. But in this lecture, we're going to talk about another inference algorithm, also known as theorem proving, and we're going to look at a bunch of inference rules that can be applied to derive a proof, which is a chain of conclusions that leads to a goal or to an entailment sentence. So we're going to have 10 inference rules, and these rules together with propositional logic that we discussed earlier is called propositional calculus. So basically, propositional calculus is propositional logic plus the 10 rules of inference. And again, what is propositional logic? It's essentially all those sentences, A, B, true or false sentences, all the connectives, and now we're going to add into that the 10 rules of inference. So now we can actually derive conclusions rather than try to check models And then this is a little bit more intuitive for humans, right? When we're trying to argue something, we want to come up with a series of conclusion, of which are logical, and that eventually lead to what we're trying to prove. And so model checking is kind of a computer way of doing this, and even the Tableau tree is more of an organized way of doing model checking, but it's essentially algorithm that are kind of program. But this way is a little more of how we human like to kind of prove things. So there are 8 non-hypothetical rules and 2 hypothetical rules that we'll learn, and then we can use these rules to derive conclusions. And again, we won't really go into this, but propositional calculus is sound and complete. In other words, by having these 10 rules of inference, we can everything is sound, and then that we also have completeness. Okay, so here's the first rule. This is called Modus Ponens, and this is a very famous rule. It's very basic. It's really this is how it's set up. This is the symbol that represent the top are the premises. So we have 2 premises: A implies B and A, and the bottom is the conclusion. And so if we have the A implies B and A, then we can conclude that B is true. And so this is Modus Ponens. And another name for this that I actually like better is called Conditional-Elimination. What that is that if you have a conditional here, and by knowing the antecedent, we can combine it and eliminate the conditional and get the conclusion. So in fact, all these rules have names that are kind of similar to this, and the name should help you kind of remember how the rule works. So I prefer this Conditional-Elimination name. Even though Modus Ponens is kind of a very famous name. Okay, for example, if you know that if A it is raining and B the ground is wet, and suppose that we have in our knowledge base 2 axioms or 2 facts. We know that A implies B. We know that if it's raining, the ground is wet, and we also know that it is raining. Then we can infer that the ground is wet. So that would be a simple application of conditional elimination. The second rule is Conjunction-Elimination. So in fact, the first few rules is all about elimination. So we try to eliminate a certain connective, and so this says that given a conjunction, any of the conjunct can be inferred. So symbolically, this says that if you know A and B, then you can infer A. If you know A and B, you can also infer B. And so we basically, again, the name here is very useful, is helpful. Conjunction elimination, that means that I can eliminate the conjunction and infer A. I can eliminate the conjunction and infer B. So here's another elimination rule. Negation elimination. If I have a double negation, then you can eliminate both of them. So not A is A. Yeah, a lot of these rules are very straightforward, and so we it's not too surprising to have these rules as rules that we can use to derive conclusion. Okay, and then if you have this is called disjunction-elimination. So we want to eliminate the disjunct, eliminate the or. If you have A or B, and we also have A implies C and B implies C, because we have A or B, one of A or B is true, and so together with these two, because either A or B is true, then we definitely will have C. So we have all these 3, then we can conclude that C is true. Here's another elimination. It's called biconditional elimination. If I have a biconditional, I can eliminate it by so if A biconditional B can be eliminated by saying A implies B and B implies A. So that's biconditional elimination. So these are all elimination rules. We try to eliminate this biconditional. We try to eliminate this disjunction. We try to eliminate the negation, and even in the first one, we try to this is eliminating the conjunction, and this is eliminating the conditional. So all these are elimination rules. Okay, and then here's the 6th rule, introduction rules. So next the 3 a few would be introduction rules. So if you have A and we have B, then we have A and B. So we are introducing the conjunction, right? So if you have A and B separately, together we have A and B. So we introduce the conjunction. disjunction and introduction. So we're trying to introduce the disjunction. So if you have A, then you have A or B. If A is true, then A or B is true regardless of what B is. In the same way, if A is true, then B or A is also true. So we're introducing the disjunction. So here's the last of the 8 non-hypothetical rules. This is the biconditional introduction. We're trying to introduce the biconditional. If you have A implies B and B implies A, then together we have A biconditional B. So those are the first basic 8 rules. And certainly we can check that these rules are valid, right? By doing the truth table if we have to, or using model checking, or etc., or even using refutation trees. The point here is that we can prove all of these to be true, and then now instead of you doing model checking with a truth table, we can actually apply these rules which we know to be true and obtain new senses to add to our knowledge base. Okay, let's do some examples and see how we can use these 8 rules to derive conclusions. Okay, so suppose I want to prove that given P and Q implies R and P implies Q, can we show that these 3 sentences in our knowledge base, can that entail R? Okay, so here's how we prove it. We just do one line at a time and just make a series of deduction. So the first 3 sentences, these are assumptions that we make. These are the premises. So we just write 1, 2, 3. We write the statements. We write assumption on the right. So we use this column proof where on the left is a sentence that, and on the right is the reason for that sentence. Okay, so now how do we get R? Well, let's look at this and see if we can combine certain things. If we know P and we know P implies Q, we can put them together and get Q. And that rule is, again, using sentence. So the reason here is that we're using sentence 1 and 3. So 1 and 3. And then we use our reasoning is the conditional elimination. This is Modus Ponens. Given P and P implies Q, then we get Q. So that's the conditional elimination. So again, on a test, you want to do this. You want to be able to write the sentences that and also the reason for the conclusion given here. Okay, so now we're going to do this again because I know Q, which is 4, and I also know Q implies R. Together, conditional elimination again, I get R. And that's it. That's what we're trying to prove. We're trying to prove R. So notice every sentence, every step is just a conclusion that can be derived, can be achieved by using one of the 8 rules. In this case, we used the same rule twice. Okay, example number 2. Suppose we have not P implies not Q, and then not P. Can we show that this entail Q? So again, these are assumptions. We always put the assumption as the first, a few reasons. And then we can use the negation elimination. So this says that I can eliminate 2 negation. So that gives me negative not P. So that's from sentence 2. And then because of not P and not P implies not Q, we can use again conditional elimination. Combine those to eliminate the conditional and get not Q. Use negation elimination again to get Q, which is what we want to prove. Yeah, so a lot of this is pretty straightforward. We know all the rules. And notice that once we do this enough, we should be able to know the names of these rules. The goal is to kind of understand that the name of the rule actually is actually very easy if you understand the rules themselves. Okay, whatever I want to prove P and Q implies P and Q entails Q and P. So that seems pretty reasonable. P and Q, that's an assumption. If I know P and Q, I definitely know P. That's conjunction elimination. Again, eliminating the conjunction. I also know that Q implies, if I know P and Q, I also know Q. And if I know Q and P, I know Q and P. And that's the conjunction introduction that we saw. So that one is not too bad. Here's another one. If I know P, can I entail P or Q and P or R? Where Q and R are any senses or any senses. So P is our assumption. I'll just put an A for assumption. P or Q, this is introducing the disjunction. So disjunction introduction. So if I know P, I should know P or Q. It doesn't matter what Q is. I also know P or R. It doesn't matter what R is. This is again the disjunction introduction. I can introduce anything if I know that P is true, if the other one is also P. And because these two are both true, then I know P or Q and P or R. And that's because of conjunction introduction. Okay, that's not too bad. Okay, here's another one. This one is a little bit trickier. Has a lot of things here to work with. P or Q and P or R. P implication S, Q implication S, P implication T, R implication T. But you look at this carefully, you notice that these chain and you can put them together in a nice way. You want to show that all these entail S and T. Okay, so the first 5 is all assumptions. And then notice now we have that because we have an and here, we can use conjunction elimination, eliminate this, and then infer one of the conjunct. So this is P or Q. This is from sentence 1. Okay, and then for the same reason we can also infer P or R. So now this is the tricky one, is that because we know P or Q, and we also know that P implies S and Q implies S. This is actually one of the harder inference rules to understand, but because we know P or Q and we know P implies S, or and also Q implies S, we can infer S. So this is actually the disjunction elimination. We can eliminate this disjunct. So that's the trickiest one, the disjunction elimination. It requires 3 things, and so we get S. And the same reason we also get T. Again, this is because we know P or R, one of them is true, and we also know that P implies T and R implies T. We know one of these is true, we must have T, and that's again disjunction elimination. Then we put them together because we know S, T, we also know S and T. That's conjunction introduction. Okay, so here's another one. Where we know P biconditional, Q or R, and also R, can we get P? Well, these are assumptions. And this one right here says that we can eliminate this biconditional. And so because we have a biconditional, we can just say Q or R conditional P. And then because we know that so let's see. Disjunction introduction. Let me kind of okay, yeah. So because we know that we know that this this biconditional elimination, and also we know that. Oh, sorry. Yeah. I got confused for a second. Yeah. So we're using 2 here. Sorry, I didn't. Yeah, we're using 2 here. Because we know that R is true, we can introduce Q, where Q could be any sentence. So this is called disjunction introduction. Yeah, sorry about that. So we do have this because of R and disjunction introduction. And now we can combine this one and 3 and 4 and get P. That's a conditional elimination. And so that's P. That's what we want to derive. Okay, let's talk about the hypothetical rules. So we have 8 non-hypothetical, which we just went over. Now we have 2 more hypothetical rules, and these are a little bit trickier, so we want to be careful how we do this. Okay, here's the first rule. This is the conditional introduction. So it says that given a derivation or a proof of B using the hypothesis A, we can drop the hypothesis A and infer A implies B, or A conditional B. So this says that if I have a hypothesis A, if I assume A temporarily and somehow prove B, then I can drop that hypothesis and infer the conditional A implies B. And then the negation introduction says that suppose that I have a proof of some contradiction from assuming A, then I can drop the hypothesis A and infer not A. Because by assuming A, I get a contradiction. It must be true that not A. It must be true that not A is true. Alright, so these are kind of a little more confusing, but if we do a couple examples, this will be actually very clear. So let's do a few more examples. Okay. So suppose to have P implies Q and Q implies R. It's reasonable that P must implies R. That's what we want to show. So again, if this is a knowledge base, we can add this sentence to a knowledge base because this is entailed by the knowledge base. And so these are assumptions. So now, so the trick here is that because I'm trying to prove a conditional, then the hypothesis, the conditional introduction is useful. Again, this is useful if I'm trying to prove an implication. Then I want to use the conditional introduction. So I want to introduce this hypothesis. Okay, so again, I want to prove a conditional. So I want to introduce this conditional. So the way to do that, we have to hypothesize P. We have to assume P temporarily. Again, we don't know that P is true, but for the sake of introducing this conditional, we're going to hypothesize that P is true. So it's just a temporary assumption. And the way we kind of denote this is that we're going to draw a line right before it to show that the next few lines, right, that correspond to this vertical line is under the assumption of P. So this is temporarily assuming P. Everything else follows because of this hypothesis. So that's how we denote that. And we want to do this in our homework and also in our test. So temporarily assume P. We're now going to do conditional elimination with P and P implies Q. So 1 and 3 will get me Q. So this is because of conditional elimination. And then because of Q at 2 and 4, again conditional elimination gives me R. So again, these Q and R, these conclusion comes because of my hypothesis P. That's why they are under this. They correspond to this vertical line. So that's gonna be our notation for that. And then now we can actually so this says that by hypothesizing P, we have found a proof for R. So by assuming P, we prove R. So now we can dissolve this hypothesis P and conclude P implies R. Right? By hypothesizing P, we can prove R. Now we can dissolve all this and infer P must implies R. So that's the conditional introduction that we talked about. That's a hypothetical rule that we just added to our a list of rules. So hopefully that makes sense. Yeah. So this again comes up whenever we want to try to prove a conditional. Then we want to hypothesize the antecedent and try to prove R. Then we dissolve the hypothesis and infer the conditional. Let's do another example. Now this will kind of help you understand the other one, which is the negation introduction. So what if I have P implies Q and then not Q? Can I get not P? So again, this is reasonable, right? If P implies Q and Q is not true, P must not be true, because if P was true, Q must have been true. So this is a reasonable conclusion here. So okay, so here we go. So this is another way of thinking about this. Is basically a proof by contradiction. We wanna prove not P, so temporarily assume the opposite. You know what? I think I'm gonna make this. I think I'm gonna add another sentence here. I think it's probably better to start out with this. I want to make a small change here. I think this is probably a little bit better. So I have to kind of modify some of this, but okay. So let's start here. So again, I want to derive this, and so a contradiction proof was to assume the opposite, assume not P. So let me kind of do this here, and so the next step. So I'm adding more sentences here now. So now I can use one of the rules that says that the double negation rule. It says that now from 3. So this is the negation elimination. So not P implies P. Okay, and then now I'm going to use for 4 and 1 with the conditional elimination and get Q. So that's the conditional elimination. And so now I want to extend this line. But notice that I have Q here and I also have not Q. So I have Q and not Q. And so under the hypothesis that let's see, make sure this is right. Yeah, under the hypothesis that that P is not true. Actually, under the hypothesis that not P is not true, we get a contradiction. So therefore, its opposite must be true, which is not P. So that means that so this is essentially a proof by contradiction. Is what are we trying to prove here? We negate it as a hypothesis, and then if we get a contradiction, then we can safely infer its opposite. And so maybe as another thing to make this even more clear, I think we should have. So again, it seems like this is making it more complicated, but I think technically we should have one more line here that says that. Now we actually should have this again. Technically we should have this, right? Because by assuming this, right, we get a contradiction. Therefore we negate this. And so this is our hypothetical introduction. So I should put this up here. Sorry about this. Adding this kind of make things a little bit more complicated here. But when I post the slide, everything here will be nice here. Okay. So again, so we have again we have this hypothesis. We get a contradiction. So there we have to negate it, and then now we have to now we can eliminate the. So this is from 7. This is the negation, elimination, and that's what we want to prove. Okay, so hopefully that makes sense. Okay, let's go to the next part. Okay, this one's a little bit more complicated. So P implies R or Q implies S. Can we entail that P implies R or S and Q implies R or S? So these are our two assumptions. So again, the trick here is that because we're trying to prove a conditional, actually we're trying to prove two conditional. So we know that we have to hypothesize not once but twice, right? The first for P, hypothesizing P, and the second hypothesizing Q. And so that's going to be the first hypothesis. Assume P. That's our hypothesis. We want to derive this, and then we're gonna draw the vertical line. Again, when we first do this, we don't know how long this is. We might have to extend it, but for now, let's say we have this line. Okay, so under hypothesizing P, what can we get? Well, again, conditional elimination. 3 and 1 will give us R, so that's one thing. And now we want to get to R or S, but we have R, so disjunction introduction will give us R or S, and now that's what we want. We assume in P we have proven R or S, so now we're going to dissolve this hypothesis and conclude P implies R or S. So that's conditional introduction. And then we do this the same thing for Q implies R or S. Hypothesize Q, and because of 2 and 7 conditional elimination, we get S. And certainly we have S, we have R or S. That's disjunction introduction. And then because assuming Q allow us to prove R or S, let's dissolve it and conclude Q implies R or S. And because of 6 and 10, we have these two sentences that we derive. We now can do disjunction introduction, which allow us to put them together with an AND. So that one's a little bit more complicated, but the tricky here is that we look at the right side, and if there's a conditional, we have to hypothesize. We have to use the hypothetical rule. Okay, here's the last example. Okay, assume P and Q implies R. Can we show that P implies Q implies S? Okay, so here's our assumption. P and Q implies R. Okay, so again, we have this conditional, so we know that we have to hypothesize. We also have this conditional, so we know how we have to hypothesize again. But this time, unlike the previous time where we have to hypothesize one after another, this one is a nested hypothesis. So let's hypothesize P. And now we want to get to Q implies R. Right? We want to get to this. So to get to this, we need to hypothesize Q. So that's another hypothesis. And because we have another hypothesis, we have to add another line. So notice this first line is under the assumption that P is assumed to be true. But if you're inside both of the lines, that you assume in P and you assume in Q. So because we have P and Q, we can now conjunction introduction P and Q. So that's from 2 and 3. And then because of 1 and 4, we have conditional elimination. We get R as a result. So now we have, assuming Q, we have R. So now we can dissolve the inner hypothesis and infer Q implies R, which is what we want. And now we notice that assuming P, we have Q implies R. So now we can dissolve the outer hypothesis and get P implies Q implies R. And that's what we want. Okay, hopefully that makes sense. In our homework, we have a chance to kind of really practice all of these rules and know how to use them. So, okay, thanks for watching.